Hello, my name is Sarah Mozinski, and I'm a freshman forensic chemistry major currently conducting research in the SPEAR Research Group as a member of the Research Apprenticeship Program here at West Virginia University. Today, I will be presenting my preliminary research on the efficacy of hyperspectral imaging and identifying latent trace signatures. First, what is hyperspectral imaging, or HSI? So HSI is a subcategory of spectral imaging that combines spectroscopy and digital imaging. It is similar to a traditional RGB camera, which can generate pictures in 3 color channels that correspond to the visible light wavelengths associated with red, green, and blue hues. However, HSI can utilize wavelengths across the electromagnetic spectrum, and in my case, our sensor was capable of collecting data from long wavelengths in the visible portion of the spectrum all the way into the near infrared, meaning wavelengths within the range of 800 to 2600 nanometers. The result is an image, but is now referred to as a data cube, because now not only does it provide the x and y Cartesian coordinates of an individual pixel, but it also reveals the reflectance data at a given wavelength, which is represented by the z depth of the cube and the variable lambda. So if you think of drilling into that cube at a single pixel, you can reveal the spectral reflected radiation intensity for that given pixel at every wavelength. Looking at figure 1, the pixel selected within the crosshairs of the image would be that highlighted pixel, and the graph represents the reflectance data for that pixel at each one of the sampled wavelengths. Equipped with this sophisticated instrument, my research goal was to test the efficacy of HSI in a forensic setting for identifying latent trace blood signatures. To accomplish this, I needed to achieve 3 main objectives: gather reference spectral data, validate a method to unmix the spectral responsive pixels, and then perform a double-blind experiment to see if I can identify hidden or latent blood signatures not easily visible to a crime scene investigator's unaided eye. Reference spectrum were collected for the main purpose of ensuring proper calibration and operation of the sensor. A sample of oil paint with previously published spectra was made and scanned. And taking this scan, we were able to generate our own reflectance spectra as seen in figure 2 and compare it to the published material. Once validated, this was useful to characterize a possible background vector in the calculations I'll detail next. Realistic forensic signatures are typically mixtures, meaning that they often contain a biological material of interest mixed with one or more forensically irrelevant profiles, where the latter can be referred to as a matrix, so for example, bloodstains found on carpet. Thus, HSI imagery is expected to contain mixed pixels. Because forensic evidence is found naturally as mixed samples, it is important that we are able to appropriately identify target signatures of interest via a spectral unmixing model. We decided to test the utility of a linear unmixing model called orthogonal subspace projection, or OSP. OSP assumes that a question vector x consists of an unknown amount of the relevant signature, vector t times a, plus an unknown amount of the irrelevant signature, b times vector f, plus some error in the model. In order to isolate the desired signature, we try to eliminate the background data, which can be done in 2 steps. So first, we create a background suppression operator. And then next, we use this operator on vector x in order to create vector z, which is a new background suppressed version of x. Finally, we try to determine how much target remains in this background suppressed version of x using a dot product. And if we repeat this entire process on a pure target vector, we can determine the maximum possible projection of target in the background suppressed space. And the ratio provides us with the fractional abundance of the desired signature in the original mixed sample. So in other words, I can determine if a mixed pixel is 90% blood or 20% blood. So in this project, a scan of blood was run through OSP calculations to calculate its fractional abundance at 7 different pixels in a mixed sample, and the results can be seen in Table 1. Overall, the tentative results indicate that this technique can identify blood targets at an abundance as low as 22%, with the overall success varying as a function of the background interference. Finally, a double-blind experiment is intended. The next step is to perform this experiment, in which a mock homicide crime scene will be set up in the WVU crime scene house complex. An example scene is illustrated in figure 3. This mock scene will be set up by another research analyst, so I am completely unaware of what the scene will look like or where the bloodstains and deposits will be situated in the overall crime scene before I go in. My job will be to collect scans of the overall scene, of which each pixel will be sequentially processed via unmixing. The result will be a spatial map of the blood's abundance, and once complete, the computed abundance will be compared to known deposits, and the ratio of correct identifications will be computed in order to report an overall measure of the performance of using HSI and OSP in a cluttered forensic scene. If successful, this will prove to be a contribution to the forensic science community, because the more hectic a crime scene, the more evidence can be included. So having a digital map of the scene will make it easier for experts to analyze bloodstain patterns in order to replicate the crime scene and figure out what happened. Thank you for your time and attention in listening to my presentation today.